think so. We're gonna start. So welcome and thank you for joining us today for this for our webinar Repair Don't Replace and how 3D scanning and 3D printing are redefining sustainability. So my name is Marcio. I'm sales application engineer at CREAT3D, and I'm thrilled to welcome you today to today's session where we will explore how 3D scanning and 3D printing are helping industries rethink sustainability by repairing instead of replacing parts. So these technologies are making it easier to extend product life cycles, reduce waste, and support a more circular economy. So please note that this webinar will be recorded, and at the end of the webinar, we will have a dedicated question and answer round. So we encourage you to write down any questions you may have during the presentation, and we will be helped to address them and provide the answers at the end. So on today's webinar, we will the main topics of this the webinar we will cover three subjects. So the first one will be combining the 3D scanning with that additive manufacturing. So we will explore how these technologies complement each other to create efficient workflows and unlock new possibilities. Second topic will be real-world applications, where we will see practical examples of how CREAT3D is leveraging these solutions to solve challenges. And then the third topic will be key scan software features, where finally we will break down the essential tools and functionalities of the software Peel.CAD Pro, so the workflow from scanned data to a solid part. By the end of this webinar, you have a clearer understanding of how these technologies can transform your process and open new opportunities for innovation. So let's get started. So before we dive into today's content, I'd like to introduce our three presenters who will be guiding us through the session: Sachin Patel, Adrian Lobo, and Joe Wilston. So Sachin, can you introduce yourself?
Yeah, hi everyone, thanks for joining. My name is Sachin Patel. I'm Major Accounts Manager here at CREAT3D. Been with the company for just over 6 years, and I support our existing customers with getting the most out of their 3D printing and 3D scanning technologies. I'm joined by my colleague Adrian.
Hi there guys, my name is Adrian. I'm the Applications Engineer at CREAT3D. My job really is to understand your potential needs and try to actually leverage them into 3D printing itself. Most of the time I try to reduce the amount of aluminium used. So we try to print out printed tools and stuff at the time. And I'll move on to Joe.
Hi, I'm Joe Winston. I'm an account manager at Measurement Solutions. So I've been in the 3D printing world for maybe 10 or 12 years and the 3D scanning for the last 4 or 5 years. At Measurement Solutions, we are the UK partner for Peel and Creaform. So work with a lot of companies from all sorts of different industries and disciplines in the UK on 3D scanning applications. And back to Marcio.
Oh, thanks. I believe that's me starting now. Cool. So I'm just going to cover up a bit about combining 3D scanning with additive manufacturing. We've got a few slides here where I will talk about how these two technologies go hand in hand. Really quickly, before I get to the next slide, just a quick introduction into us, into CREAT3D. CREAT3D, essentially, we're a team of engineers. We work with UK manufacturing and engineering companies to help improve efficiencies, problem solve, and the technology we do that with is 3D printing. We supply 3D printers, we supply 3D printed parts, but also we're doing, as you'll find from today's webinar, we're doing a lot more with 3D scanning. So we work with MSL and Peel to offer 3D scanning solutions as well. Next slide, please, Marcio. Cool. So I'm going to talk a bit about the benefits of digitalization. So we're jumping right in. Essentially, digitalization, we're talking about the tools used for the practical and accurate capture of physical geometry into 3D data. One of those tools is 3D scanning. The great thing with scanning, there are a number of benefits. One of the key benefits is saving time. So we're able to, with peel scanners, scan in minutes, removing the need for multiple manual measurements, any kind of human error involved in that. With scanners, we're able to scan objects within minutes, taking that physical object and creating data from that object that we can then manipulate, repair, and save, and continue with, as we'll see, 3D printing or manufacturing in other ways. This also works as a solution for waiting whilst we're waiting for parts to arrive from suppliers. Scanning allows us to scan components within minutes rather than waiting for long lead times with suppliers. Creating an exact fit. So often, going back to this idea of manual measuring, the mistakes can happen. It can be difficult to get accurate measurements from existing physical geometries. Or it can be difficult or impossible to do this kind of stuff in CAD. By having scanner, we're able to scan physical geometry and get an exact fit of the components that we have in physical space. Documenting digitally, we are working with a lot more clients these days who are looking to digitize their warehouse, digitize their spare parts inventory. What we're finding is that there are huge costs involved with storing components physically in warehouse space, when actually only a few are required, or you've got large minimum order quantities. What you can do with scanning is you can scan spare parts, spare components, and actually keep them stored digitally and only print and manufacture them when required. And that ties into saving money as well. So again, no minimum order quantities. OEM components, spare parts, often there are minimum order quantities when you need one or two or a small batch. The great thing with scanning and printing is that we're able to scan and only produce exactly what we need, whether that's one or a small batch of components. We're also reducing downtime for any broken machinery as well. And reverse engineer. So scanning allows us to take a component that may be damaged, maybe obsolete, maybe a component that you've never had a drawing for. It may be an OEM part where you can't get access to certain data. Scanning allows us to capture that data. Next slide, please. So some of the uses of 3D scanning with additive manufacturing or 3D printing. Like I said, it's a practical and accurate solution for capturing physical geometry of existing components, especially when original data is unavailable, outdated, or it's too complex to measure in CAD. One of the uses is for maintenance repair operations. We can fix at speed and at a low cost rather than disposing of components. We're able to repair them. Another thing we tend to notice on things like production lines is workarounds and components that have been quickly manufactured to solve a problem, but they're not necessarily the best solution. Scanning enables us to create a replica of that physical object, and then 3D printing allows us to create a very close like-for-like to the original component. Restoration, that we have an example that Adrian's going to cover a bit later in terms of some of the ways you can use scanning for restoration projects. We work with prop, film, TV design companies, as well as sort of architecture art, where you can scan some of these original artifacts and then create a replica or a 3D printed version of that. Like I said, digitalization, capturing detail of physical parts to create digital twins. So having a backup in the cloud of a physical part so that it's there ready to be printed when needed. Customization. So again, these OEM parts that are on a production line, it may be that for what your needs are, you need a slightly better or slightly different component. With scanning and 3D printing, we're able to scan the original component and take that data, manipulate it, and create a customized version of what we actually need. And then finally, validation. Scanning allows us to quickly validate components, scan, and then test out form and fit. Next slide, please. So some of the reasons why we combine 3D scanning with additive manufacturing, we know these two technologies go hand in hand. Like I said, there's a huge time saving involved. We can go from a problem to a solution very quickly. There are fewer workarounds and less estimating. Going back to this idea of manual measuring, well, actually we can scan a component, we get an accurate representation of that part, and then we can print and we can test and we can iterate. There's less trial and error involved, and we're able to edit and redesign data simultaneously. Saving money, we often talk about bringing technology in-house. You know, you've got greater control, and there is a cost saving with having this technology in-house rather than outsourcing. You do lose some control. You have that reliance on external suppliers. But actually bringing all of this technology in-house, scanning and printing, you're able to have full control over your data and over actually manufacturing the parts as and when you need them. You can create multiple iterations of a component. You can scan multiple iterations, and you can print multiple iterations. And you've got that immediate testing and validation, and your 3D printing, your manufacturing at a fraction of the cost of manufacturing that part any other way. It is much more sustainable as well. So we talk a lot more about becoming local and not global. Again, going back to this idea of less reliance on suppliers, no minimum order quantities. If you need one part, you can scan and you can print one part. You don't need to be ordering lots of components in from a supplier, holding up warehouse space. All of your files are stored digitally and printed as needed, and producing and better end results. So again, reverse engineering and customizing your parts to get better solutions. Next slide, please. Cool. And then finally, I just wanted to talk about printing technology. So at CREAT3D, we work with lots of different types of technologies, right the way from sort of filament-based 3D printers, resin. We have a range of different polymers and metals that we can print in. When it comes to scanning, the technology that we think kind of goes best hand in hand with 3D scanning is selective laser sintering. So this is where we're using powder to build components layer by layer, and we're sintering that powder into a fused sintered component. The reason it goes hand in hand is that we have true freedom of geometry with selective laser sintering. With other 3D printing technologies, we have to consider our support material as our component builds. With powder technology, our components are suspended around unsintered powder. So we don't have to worry about support material. We can efficiently print complex geometries without the need for support structures. So this is really important when we're scanning things that may have been injection molded or machined, where those parts have been designed for that manufacturing technology. With selective laser sintering, we've got much more freedom for putting those kinds of geometries through a 3D printer. There's less design for additive, you could say, that needs to be done. It is a seamless workflow. So as you'll see a bit later on, we can take scan data, work that right the way through to the printing software to then be printed. We are creating strong and functional parts. The component you see there was printed in nylon 12, which is a strong, durable material. There are a range of different powders we can print on the Formlabs Fused SLS printer, depending on your application, depending on those material requirements, if it's heat resistance or chemical resistivity. There are a range of materials that we can print with. It's an accurate technology, so we can produce exact fit components. It's great for low volume, but also if we ramp up into batch production, it's a great solution for those kinds of applications. Fast turnaround, so again, no reliance on waiting for external suppliers. The lead times have dropped right down so that we can print on demand as and when we need, and lower cost, of course, with this technology. Next slide. I think that's me.
John, we have
yeah.
questions
Any
here.
questions?
Yeah. So we have one. How much time spent you at the model to bring it in the print software?
Sorry, could you repeat that, Marcio?
How much time did you spend at your model to bring it in the 3D print software?
Right. Okay. So it varies. Typically, we say with scanning, to get the scanner ready, to set up your environment and scan a component like we had on that previous slide, you're looking at anywhere sort of 15 to 20 minutes. Now, with that specific part, Adrian's going to talk about that part in particular in a couple of slides. It was a broken part, so in terms of then cleanup within the scanning software, we had to clean the part up a little bit, or clean the scan data up, I should say, and then the broken elements of the original component were then repaired in the CAD software. So that was another 30 to 40 minutes of cleanup work. So within an hour, we're able to scan a component like that, take multiple scans, combine those scans, repair the part, and then from there we can export that file into CAD data, or even a step or an STL file, which would then allow us to print that directly through our slicing software, which the printer is back here. All of our printers have dedicated slicing software. You take the file into that software will allow you to create a print ready file. So really, scan, clean up, you're looking at an hour. To get your printer ready, another hour or so. Within a few hours, you should be able to get a part in your hand from scan.
Okay. And we have another question here. Why did you use SLS printing to produce the parts?
Yeah, the main benefit, I would say, is freedom of geometry and freedom of design.
Yeah.
You know, we don't have to worry about support material. We are creating mechanically strong or uniform components that are uniformly strong. And yeah, nylon 12 is a durable material. So for our application, it was ideal. We knew it would withstand some of the knocks it might have gotten from our engineers using the equipment, but also there was some heat resistance we needed. So actually, it kind of ticked all the boxes for us, the material and the process.
Maybe another question maybe more for Joe. What file format are these scan files output in? And
So if we
yeah, I'm sorry. Go ahead.
so the raw scan data, it's all scanned in a point cloud, then we would convert it to an STL. If we're going straight to a print, so if we're just trying to replicate a part that's there, a physical part that's there, we can just scan, export that as an STL, and that will go straight into Slice software. If we're doing modifications or trying to reverse engineer or build a parametric model from the scan data, then we can export out as a step IGES file. And I believe some of the software that you guys have got for the Fuse can take native CAD files as well, so we don't necessarily need to do the conversion to an STL before we print.
Yeah.
Thank you, Joe. I think we have all the questions there answered.
Okay, cool. So moving forward, we will look at some of the applications now. Now, with the application, these are more tailored to CREAT3D itself. However, these are not limited just to CREAT3D. So we have a few videos and a few slides about this thing. So if we go on to the next slide, we can start with the first one. Right. So the first one is to do with restoration. Now, this mainly applies to art, history, museums, heritage, and stuff like that. The reason and the difficulty where it comes traditionally is when people have to actually fix an existing piece of equipment, they will have to actually measure or hand measure those details on there. Now, once you do that, so say if you look at the first pattern on the second slide, on the second photo below, they will have to actually hand measure those details. And when you're doing so, you may possibly damage that particular part as well. With 3D scanning, you can literally go around that part on that section and then mimic or copy that geometry to then apply it to the broken piece itself. Now, with 3D printing, you do get the parts made in a standard color. However, you can post-process these parts to actually have a good finish in the end. The video on the second slide is going to show you how we've actually started from that original point to actually end up to the second slide, second image on the bottom. So if you go on to the next slide now, we have a look at this video whilst it's going. And I'll just comment over it as well. Yeah, so this is the broken piece that we have on our screen, and then we've got these target points that we're putting on there. Now, essentially what these are is actually for the scanner to identify the platform itself. You can see that the scanner is moving around the part itself. It's taking up on that data. Once we've got that data, we've cleaned it up onto the software, make sure everything is okay with it, there's no water holes and stuff like that. Once we're happy with that, then we can then convert that into an STL file to then put into Preform. Now, this is Preform software for the Fuse One system itself, which is the SLS. We placed it onto the printer, let it print overnight, got the parts out from that chamber, have the parts cleaned, and these are just the post-processing steps to it. Now, the good thing with the SLS system is that you can put in one part or you can put in 1,000 parts if you need to, depending on what your actual, your final product needs to be like. So we've just cleaned the parts over here, and then after that part's been cleaned, you can see that it's also then painted to actually meet the color of the board itself in the first place. And this is how you can actually try to fix or repair existing pieces of equipment, especially for heritage. Now, the good thing with one of these things is that obviously we've just printed that part. What you can also do is actually create a mold from that particular scan data, and then pour in concrete or anything else as so to mimic the original look of that particular file itself. Now, that is one particular example. Now we can look at the next one. If you go to the next slide. Yeah. So this one is for bespoke bracketry. Now, many times when we do get pieces of equipment, especially like large units, like the one that we're looking at right now is actually for a generator itself. Within that generator, there's loads of tubings, cables, and stuff like that, which are just abruptly left inside. When it comes down to maintaining, or when a service engineer has to go down on site to have a look at it, all these tubes do tend to come in the way, and it makes it a bit difficult for the user to actually work on. What we've done actually is we've scanned the entire generator itself and then managed to actually input in touch points. If you look on the second image down there, you can actually see a jig which is actually holding these tubes in place. Now, realistically, if you have to do this on a traditional approach, you would have to have an engineer actually sit there and then measure those points internally, which might be quite difficult to actually get your hands in with it. Having the scanner available now allows you to actually just get that data in one go itself. Not only that, but now once you've got the entire scan data of the entire generator, it also helps in actually planning where you want to position the generator in a room as well. You do also get large size scanners where you can scan a room, find out how much space you've got before you actually have the equipment in-house as well. It's another good approach. If you look at the video now, we go through the steps on how that was done, so you get a better understanding of how it's actually worked through. Yeah. So with the, as you can see now, you can see the tubes which are loosely hanging in place. We've got the scanner scanning around the entire geometry, and we're trying to pick up as much as we can. Once you've got that data in there, if the data isn't actually good as well, another point to mention is that you can also take multiple scans of the same file and then merge the two together. So this is what we've done in this particular video. We managed to see what the tube diameter was, and then we've designed a tool in CAD itself and then printed it on an FDM printer, as you can see. Once we've got that file out from there, we then attached it to the compressor itself with some screws. And then that holds the tube in place. It just makes it a bit more neater and safer for the user to operate with. Okay. And I think we've got one last one. On to the next slide. Yeah. So this one is actually a bit more applicable to most of us in our industries. Now, what we've got here is a broken pump housing, which has happened because of usage or due to dropping down or harsh use itself. When those things break, and especially if they're important items, they then tend to cause an issue in the production line where things have to halt or you need a replacement to come into play. Being able to scan this part now actually allows you to have a scan data of that particular piece itself and then print it as and when you require it. Normally, to get this part made, you would have to go outsourcing it, and then you have to place a minimum order quantity to get something of that. Say for this example, you'd have to place an order for 4 of them just to get 1 of them, and that remaining 3 tend to stay in stock itself then, and you're just holding up stock all the time. And from what we've learned from previous experiences is that holding up stock also takes up money and time as well. So in this particular example, if you look at the housing there, that housing cost us only about £4 to make, and that was made within a day's time actually. We'll see in this video now how that actually applies and how we've actually gone through doing this particular process, and then we'll see how it actually affects you guys as well. Okay. So this is the generator that I was talking about, and if you look at it, that is the section which is broken. Now, the reason why this is an important part is because that doesn't allow dirt or loose air particles to actually accumulate into the filter itself. So you can see that actually could degrade the compressor's durability down the line. So we put some few target points on that sticker on the broken part itself, and then have the part scanned. So you can see the scanning is going on at the moment. We've got that data picked up onto the software. Once that data has been cleaned up, processed on Peel software itself, we managed to identify what we actually need to fix first. We then changed that onto CAD, fix the data on there, and then apply it into Freeform again back inside. The printing process is exactly the same for the last 2 technologies, so we've just gone through that. take the loose powder out. The loose powder goes back into the system itself, so you're not actually wasting any powder as well. And then you just finally clean the part up with some compressed air and media beads. And then you can look at it, like you can see the new part and the old part together, and then that's actually joined in together to fix back to the compressor itself. And that's how quickly you are able to actually get parts onto your compressors now. Yeah, cool. Next slide. Yeah. So we've seen a few examples now. We've kind of related to where they actually fit in within each and every one of our industries. So the first few, which was in restoration side, kind of affects inside the arts and history side. Then the bump housing works mainly towards the automotive and MRO and engineering side. Now, obviously, we've used the principle, these technologies, to get these parts made in-house, but we're not only limited just to using the SLS itself. The reason why we've gone down the SLS route is to basically get something without any support structures around the parts. The reason why we did so as well is because if you did have support structures on the part, that sometimes may tinker the actual finished geometry of your part. So say if you've got a really important surface that you need to make sure that it has to be correct, having supports on that particular section could actually disorient it from what you actually want it to be like. And that's why the SLS works best in that side of things. The scanning side works beautifully across all the kind of technologies, but ultimately it comes down to what you actually want your part to do or function towards the end. With the scanning data with the house pump as well, you could also actually try customizing it to actually put in further details to it if you want to. But for the purposes of what we needed it to do, we just needed a replica of it. I think that kind of covers in what we do in the terms of application that we've kind of covered at Created itself. But I think it's something that you guys should also ponder upon to see where this actually could fit in within your business as well. That's it for me for now. I'm going to transfer this over to Joe to look at some of the details on the house pumping side itself.
Thank you, guys. So yeah, we looked at the compressor housing just now. We saw the process of scanning it, the process of building it. So I'm just going to touch on that kind of bit in the middle. Something that's often overlooked in scanning. Within the scanning workflow, speaking to our customers, we know that in scanning, probably only 15 to 20% of the time is actually spent scanning. The rest of the time is spent in the software. So it's very important that we've got a software that's nice and easy to use and integrates really nicely into our workflow. So if you've done a lot of reverse engineering before, you'll probably know the limitations in working with large STL files in CAD packages. And that was traditionally the workflow was take your scan data, drop your big STL file into your CAD package and try and design around that. So we've tried to create a bridging software almost. So the Peel and Careerform software is very good at working with STL files, working with CAD data. We can very easily extract the entities that we need to go into our CAD package. And with the Peel Pro software, we can now create actual CAD models, parametric CAD models in the software itself. So if we can run through the video, or just talk through the process that goes into that. So with our original scan data, we're going to start to create some entities. So first, we're going to create a plane. We're going to extract a surface extract a plane from a flat surface. We're going to create a cylinder as well. So we're just going to click on the sections of the scan data that make up that cylinder. You can see we've made a cylinder there. The next thing we would do is make a final plane, and we're going to use this to orientate the part. So at the moment, the part is just sort of at a random point in space, but we need to make sure that it's aligned to an origin point. So you can see here, we can select the cylinder, make the cylinder our Z-axis, select our first plane, make that our XY, and with our final plane, we're going to lock all 6 degrees of freedom, lock that into the YZ. We can also flip those planes as well. So if we want the Z-axis the other way around, we can just flip the other way. So very important to do the alignment. It's going to make our downstream activities a lot easier. So once we've created our entities, we are going to start to create some sketches. So I can run a cross section through the part, and then I can use my sketching tools in the Peel Pro software to just start sketching around that cross section. So we don't have to make it super accurate at the moment. We can go in and dimension all of these up afterwards, but we're just going to use our line tool here to sketch around the cross section to start to build up the basis of our CAD model. We have profiles, we can draw lines, arcs, fillets between lines. And like I said, we can go in and dimension all these up afterwards. We also want to make sure that everything is constrained, so we can go in and add vertical, horizontal constraints, coincidence, concentrics, equal distances. We can do all that as well to make sure we've got a very robust sketch so that when we edit it further down the line, we're going to keep a nice robust model. So again, we're just going to roughly draw around these little fins on the top of the part. I could draw the arcs in at this point, or we can add fillets to the CAD model a bit further down the line. So once we've finished all these, we're going to go into our revolve tool. So we're going to start to actually make the 3D CAD model here. So we will exit out of this. We're going to pick a center axis. When we go into our modeling, we'll go into revolve. We're going to select our center axis and our profile and do a full 360 revolve. So the revolve is ideal for parts with rotational symmetry, things like shafts, pulleys, cylindrical bodies, and great for damaged parts. So in this instance, we've picked a known good cross section of the part, revolving it 360. We've got rid of that damaged section that's in the original part. So now we're going to do another extrude this time rather than a revolve to create the internal geometry of this part. So we're going to use our circle tool, circle by 3 points. We're going to select the line. We can interact with this sketch profile. We'll do the same again, add another circle in here, and start to build up a sketch that we can extrude down to create the internals of the part. We want to make sure that we've got a clean and parametric solid body. And by making something parametric, we can make sure it can be modified further down the line. And here we're really transitioning from a kind of a dumb scan data that we can't really do anything with to a fully parametric model that we can dimension up and edit further down the line if we want to make any changes to the part. Also with the original scan data, we've kind of baked in our manufacturing tolerances. So anything that should be a perfect 90 degrees probably isn't. So that's why we're going to recreate it in CAD and make sure that everything is at the exact geometries that we need. So we can extrude that section up to make the internal of the part. And we can create this final section with another extrude. So again, we're going to select a plane. We're going to drag the plane out to create a cross section of the section that we want to extrude. At this point, we've got a kind of an extra geometry in that cross section, so we can adjust the plane to make sure that we are just getting a cross section of the area that we need. And again, we go into our sketching tool, and we can use our rectangle tool to start sketching out exactly what this cutout is going to look like. You can see as the lines go from green to yellow, that means we're kind of selecting on the line, so we can interact really nicely with the sketch of the part. Again, we're just going to loosely put these in the right place, and we can go in and dimension and to constrain this sketch a bit further down the line. But for now, we will just create a profile that we're going to extrude. Like your traditional CAD package, we can extrude in multiple directions. We can extrude two sides, we can extrude equally. I'm going to click on the section. We can either type in the distance that we want to extrude, we can click on the face of the scan data and have it extrude up to that face, or we can just drag the arrow to extrude it the exact depth that we want. We can also cut as well as extrude, and we have a lot of surface modeling options as well. So we talked about either putting the fillets in ourselves or going in and modifying the CAD afterwards. So now we're just using that fillet tool to go in and fine tune those corners, add some nice fillets and blend radiuses onto those sharp corners. The next important thing to do is compare this CAD model that we've created with the scan data that we had in the first place. We want to make sure we validate our model. So we've got a compare tool within the Peel Pro software. We're going to type in the range that we want. So we've typed in 0.25. So anything in green now is within 1/4 of a millimeter of the original scan data. And we can see some areas that are slightly out. So we're now able to go in and tweak those when we do our dimensioning up at the end. The final thing to do, once we've got the 3D model complete, we can either export that as a step or an IGES file. With SolidWorks, we can actually take that design tree that we've just created in the Peel Pro software and bring that full design tree into SolidWorks and make it fully editable in SolidWorks. Otherwise, if you're working with other CAD packages, you would just either save out the step file, bring that step file into your CAD package. We can also transfer just entities. So if you do want to do your modeling in Fusion, Solid Edge, whatever else, we can extract those planes, those cross sections, those entities, drop those straight into your CAD package. So you're working with sketches and planes rather than trying to work around complex STL files that can make the software quite laggy. Yeah, I think that's all that I wanted to go through on that.
Thank you, Joe. We have a question here. Why is being remodeled? Can you just import the files into SolidWorks?
In terms of the part that we just looked through there, or just in general?
Just in, I think it's in general.
Yeah, so yeah, I guess if we had a part that we just wanted to recreate, then I mean, you wouldn't have to go through SolidWorks at all. We can create the scan, take that STL file straight into a print software and reprint it. If we're looking to reverse engineer, which we've done with this part because of the damage, we can do that in the Peel Pro software, like we just saw, create the CAD model in there. Or like I said, we can take those entities, take them into SolidWorks and do a reverse engineering in SolidWorks.
Thank you. And we have another question here. What level of accuracy can you expect from the handheld scanner like the Peel 3D?
So Peel 3D has a point accuracy of 50 microns and a volumetric accuracy of 100 microns per meter. So yeah, on a small part, you're going to get 50 micron accuracy. As you spread out over kind of a bigger area, you're going to get a build-up of a tolerance over that volume. There are some kind of tricks and tips to keep that to a minimum. So for example, if you're scanning a whole car, you wouldn't want to go from one corner, start in one corner and go all the way to the other, because you've got a big build-up over that tolerance by the time you get all the way around. So instead, we'd start in the middle and work our way out almost like a spider web, so that your origin in the middle and you're building out your volumetric accuracy from there. So there are a couple of little kind of tricks and tips that you can implement to make your scan as accurate as possible.
Another question here for you, Joe. Can you integrate the scanning data into existing CAD models or assemblies?
CAD models and assemblies. Yes, so we can, if we're creating the model in Peel Pro, we can export that out as a step file or an IGES file. You'd be able to take that into your existing CAD package and build it up into assembly. So do your constraints and your assembly functions in there.
Okay. So yeah, the other one. So for example, can I just fill the holes and then reverse engineering in SolidWorks, or edit the model, like inserting holes or something else?
I think, can you add extra features? Is that?
Yeah.
I guess what's
yes,
in SolidWorks. So we can, taking the example that we've just been through, we could export that whole design tree now out into SolidWorks, and then we could carry on doing design work in SolidWorks. So we could add sketches for cutouts, etc. We could also do the same in the Peel Pro software. So we can put a plane on a surface, add a sketch, and then cut through to create cutouts and slots if we wanted to in there, and then yeah, either export that full design tree into SolidWorks or just export the step file or the IGES file and take that into your CAD package.
Another question on scanning. When the guy was trying to scan the motorcycle chassis, and then there is some noise on the scan data, how can they remove those noises?
So we've got a couple of tools within the Peel software. There's a filter for isolated patches. So by default, it's set to 0, so it will keep everything in your scan. By ramping that up, and it's a percentage, you're increasing the size of noise that's removed. So if you were scanning a motorbike, for example, everything that's attached to the motorbike would stay. If you put your remove isolated patches, if you put that slider up, it's going to remove any bits of noise. That if you put the slider up to 50%, it's going to remove everything that's 50% or smaller of the size of the main thing that you're scanning. There's also a more manual way of doing it. If you're a bit worried that it's going to delete things that you don't want it to delete, we can use our selection tools in Peel to just select everything that's connected. So you'd click the main chassis of the motorbike, anything that's connected would show up in yellow, and then you just remove everything else. So yeah, a couple of a manual way of doing it and a very automated way of doing it, but the cleanup operations are very, very quick in the Peel software.
We have a question for Sachin. How much does it cost for scanner and the 3D printer?
So scanners, the Peel scanners that we've been talking about today, start anywhere from £6,000 to £7,000. For that's just the scanner only. The software that Joe's been running through, the ProCAD software, that with the scanner you're around £11,000. That's really everything you need to do the full workflow that we've been talking about today, and all of the editing of the data, the scan data, and the CAD amendments as well. In terms of printers, I mean, it varies. You know, we supply lots of different technologies. We're talking about the Fuse selective laser sintering printer, the one behind me, the one we've been talking about with a lot of our examples. The starting cost for that printer are around £25,000. For the kind of full solution, you're at around £50,000 to £60,000. So yeah, there's lots of different technology, lots of different costs. The way we work, I think I mentioned this at the start, is we work with companies to understand your applications, understand the cost savings, the kind of efficiencies, the lead time reductions. We kind of start with those conversations. The great thing with 3D scanning and 3D printing is we know that there are cost savings, there are benefits and efficiencies to the technology. So we start with that, and often we can uncover these kind of costs that you could be saving, which really help to then justify investing in the equipment. But yeah, I hope that answered the question.
Yeah, just to add on to that as well, actually, is even with the printing side, we are also happy to actually do the printing for you guys as well, rather than actually having the equipment in-house. So we do offer that as a service in-house as well. Not necessarily just with the SLS behind us, but also with resin and FDM solutions as well.
And the same on the scanning side as well. So we can offer scanning as a contract service. So if you're just looking to get into that reverse engineering workflow, you've got something that you want to try out, scanning and then printing, then we can kind of do that service as a contract rather than making to start with. If the initial investment is a little bit scary, we offer that kind of stepping stone towards showing you the value before you fully commit to it. Yeah.
Thank you, guys. The last question we have here: what were the downsides, difficulties you had in any of those the projects you have done?
Okay. So with the application project that we were working on, I think the main downside was really not like the lack of information actually that I had at the time. There's loads of data that you're working with at the time, so to begin with, you may feel a bit daunted about it. However, one of the main things to get your head around is actually having your environment set up correctly. So the way where you're actually going to start scanning your parts in. You don't want to be in a position where there's direct sunlight altering into your scanning zone itself. So you want to be in a nice clean environment, good structured light as well, and then you can scan the parts easily from there, because any reflective surfaces can also do pick up sometimes, because then it creates a lot more additional noise, which then you have to spend more time cleaning the part itself. Reflective surfaces, another one to also talk about is to avoid having those. Say if you want to scan a glass, for example, we do have something called as a scanning spray, which you can actually apply onto the part, which actually makes it a bit more opaque. And then you can actually scan the part and get that data more clearly as possible.
Thank you. Thank you, guys. I think we have maybe if the people have some other questions, then you can just send us an email, and we can answer by email the questions. So you can send to hello@peel3d.com, and then we will be glad to answer the questions by email. So thank you, guys. Thank you very much, and thank you for being part of this webinar. I hope you get some value information. So thank you. Thank you, Joe. Thank you, Adrian, Sachin.
Thank you.
Thank you. Thanks, everyone.
Thanks, Marcio. Thank you.
Thank you.